So now we are going to learn about the Newton's laws of motion. The Newton had stated the three laws of motion, in which he stated his first law, in which this law is also known as the law of equilibrium, in which he stated that every body tends to remain in the state of rest or emotion and until an external acts on it. जैसे कि f 0 and duration of in the second law he states that uh, whenever f external is not equal to 0, then is equal to mass into acceleration. In the third law, he stated that for every action there is an equivalent. It's considered as an isolated system in which the f external is in the second law, when the f external is not equal to as mass into acceleration. And in the third law, in which he stated that for every action and there is an equal and opposite reaction, when suppose this is a wall and a ball hits the wall with some velocity, it returns back with another some velocity, which states the third law. Uh, we are also going to know about the free body diagrams. What are the free body diagrams? Free body diagrams are the applied forces on the body, all the applied forces on the body. For example, whenever an object is kept on a surface, mg force acts on it. The mass of the block is suppose m, then mg force acts on it, and also the normal reaction acts on it. Uh, some components are also used to divide these factors. Suppose in these are the two forces, their resultant is in this direction, resultant r, and suppose this is theta, then the force in this side is equal to r cos theta, and in this side it is r sin theta. Uh, in an inclined plane, the force of an object acts in this direction as mg sin g sin theta, and here the mother force mg, and on opposite to the surface it's perpendicular acting mg g. Now we will see the applications of the Newton's laws of motion. Newton's first law of motion is used to find the tension in the string. Suppose example, uh, suppose this. When a mass m1 is attached to a string and another mass m2, and m1 is suppose m1 and m2 then first law of Newton is used to find the tension in the string. Suppose this is the T1 and this is T2. Whenever the string changes, the tension also changes. Uh, we can find the tensions in the string by drawing their free body diagram. The free body diagram of 2 kg block is continue 2G downward and normal reaction upward. And also the tension T2 acts on it of block M2, and the free body diagram of 5 kg block Mg acts here, and here is tension T2. uh, by finding the tension in the 5 kg block, it is T2 equals to Mg, which is 50 Newton. And by this we can find tension in T1, which is equals to mg with 2g plus mass of this block m2g, which is 20 plus 50, which is 70 Newton. Now we will see the application of in which always F external is 0, is not equal to 0. And the Newton's second law is used to find the acceleration by using F is equal to ma. Examples are the normal reactions between the two blocks, and in which the acceleration is equal to net force on it upon mass of the object. For example, the third law of motion Newton's, it is generally used to solve the gun problems regarding whatever the after whatever hit an object about a distance from it. Now we will uh, learn about a system. What is a system? What is a system? The example of a system is, suppose this is M2 and this is M1 block, and here these are attached by a string to the block of mass M3. Here's the surface, and when this block is pulled by a force F, we can consider the following diagram as a system by taking uh, a combined system of M1 plus M2 plus M3, in which the force is applied, a certain force is applied, and acceleration is taken as common. From this we can conclude that here acceleration is equal to F net, which is upon masses, which are M1 plus M2 plus M3. Whenever to find the tension in the string, we can consider M3 as a string also by taking M3's free body diagram. Here's F, its acceleration A, and here it is tension T. From this we can find the tension in the string by taking T is equal to F minus M3A. Now we will see the examples of pulley system. We learn about system. Now we will see about pulley system. Mm, Suppose this is the diagram. Its mass is small m, and here's another object whose mass is capital M. First, we can conclude that the free body diagram of small m is mg acting shear downwards and tension in the string tension, and of second block we will consider as capital M. Here it acts mg, and here's tension T. And we can draw the free fall diagram of the pulley as uh, here's the pulley. This is here it is tension T, here is tension T, and here's tension 2T. From these diagrams, we can get some important conclusions, as the acceleration in this case is acceleration is equal to G into capital M minus small m upon m plus m. And to find the tension in the string, the formula we get is 2 capital M small m G upon m plus m. Uh, from this first diagram, we can conclude that the tension minus mg is equal to ma, and from second we can get mg capital mg minus t is equal to ma. Mm, Suppose we take an example, here say pulley. Here it a mass of 2 kg, and here's a mass of 3 kg. Tension T, tension T. For finding the tension in the string, we can use any one of both the formulas. Suppose we consider the free body diagram of 2 kg block. It will be downwards 20 Newton. The formula is tension T minus mg, which is 20, is equal to 2 into acceleration. So first we have to find the acceleration. To find the acceleration, we can use this formula, that acceleration equals to 10 into m 3 minus 2 by 3 plus 2, which is 10 by 5, which is 2 meter per second square. So we get here acceleration of the body. Hence, tension is equal to 2 into 2, 4 plus 20, which is equal to 24 Newton. We can use any one of the block. We can also use 3 kg block, also 2 kg block. Now we will learn about inclined plane. Inclined plane. In an inclined plane, when an here's the angle theta, here is a block of mass m. Mg force acts perpendicular to the ground, and here's mg sin theta perpendicular to the inclined plane. The force acting is a mg cos theta, and the normal reaction also acts perpendicular to the block itself. we can we get two equations, which is F external is equal to ma, and we also get here, when the force acting here, we get F is equal to mg sine theta, and hence ma, from this we take ma equals to mg sine theta, hence get cancelled, and hence the acceleration of the block we get is g sine theta. We will learn about some of the pulley tricks here. Pulley tricks. Here's the pulley. Here's suppose the velocity of this side is v1 and velocity of this side is v2. Here's vc. From this we can conclude that the velocity of the vc is equals to v1 plus v2 by 2. In this we should notice that all the velocities will be acting in the same direction, and suppose we take an example. This is the pulley. Here's a pulley. Here it is a mass of A, and here it is the, here it is another block B. Uh, the string is same throughout the system. Yes, tension T, tension T. Yes. The tension at this point and this point is 2T. So we will see the free body diagrams of all these. Suppose this is pulley 1 and this is pulley 2. So we will see the free body diagram of block A. So the free body diagram of block A is tension T acting upper side and force MAG. The free body diagram of the block B will be the tension 2T acting this side and force MBG acting on this side. The free body diagram of the first pulley will be like this. Here it's tension 2T, here it's tension T, and here it's also tension T. And the free body diagram of second pulley will be here it's acting the tension 2T, here it is tension T, here it's tension T. So we have seen the free body diagrams of the pulleys and the blocks attached to it. Now we will see the constant motions part 1. Constant motion part 1. Here we have to always consider that whenever there is a pulley and a string is attached to it, when we release a pulley by distance x, the string release is always 2x. If pulley moves x, then string release is 2x. Now we will learn about the when the when the string has a some mass, such as it is a heavy rod or heavy rod which has a mass. Suppose this is the diagram. Here's a block of mass M. The length of this rod is L, and some points are here: A, B, and the C. Then the tension at the point A is equal to the mg, and tension at the point B is equal to the mass of the rod is m. The mass of the rod is m. Here then the formula is m plus m by 2 by g, and tension at the point C is capital M plus small m g. Hence we can conclude that whenever the string or something used has a mass, the tensions changes in the string. From this we can also conclude that tension at point A is less than tension at point B, which is also less than tension at point A. The maximum tension is at the point A. In this we also has learned about the Lami's theorem. Lami's theorem. Here's the diagram. The force, head force, which is suppose F2, which is this is F3, and here it's acting F1. Every force has its direction. By using the Lami's theorem, it can be said that the suppose the force acting F3 acts here, we can take a common point for them. This is suppose F3. Then we can take F1. We can shift F1 parallelly here. This is F1, and we can also shift F2 here. F2. In which these are the certain angles. This is angle suppose A, this is B, and this is C. Then from this Lami's theorem we can conclude that suppose F1 upon sine of A is equal to this F2 by sine of B, which is equal to F3 by sine of C. And we get another conclusion that F1 plus F2 plus F3 is equal to 0. We will say the some examples of the normal reaction. Normal reaction is the force which always acts perpendicular to the contact force. Whenever it is an object, the normal force always acts perpendicular to this contact force. So we will see some examples in the elevator. Suppose this is an elevator. Here's the person standing in it, and when the acceleration of the elevator is 0, the force acting here mg. In this case, the normal reaction is mg is equal to mg. And suppose we consider the elevator is moving up with the acceleration of a, and mg force is acting here. Then from this we can conclude that the normal reaction on it is mg plus a, mg plus a. Suppose this is case 1, case 2, and here's case 3. When the elevator is moving down with an acceleration a, here's the force acting mg. In this case, the normal reaction on the person is, normal reaction is equals to mg minus a. From this we can conclude whenever a person is moving up with the elevator, we can conclude that the apparent weight of an elevator apparent weight of an person in the elevator is more whatever it is, and while moving down it is less than its original weight. Now we will learn about the string and spring. What are the strings and spring? The difference between them. First of all, the string. The string, in string it is considered as only pulling force. Only pulling force in which a certain object is pulled by a string. In this, the forces are only transmit. The forces are just transmit. Whereas we consider the spring, spring is both pushing and pulling force. Pushing and pulling force. And it also stores and transmit the force. We had taken the examples of the string. Now we will see some about spring force. So spring force. So we will see what is the spring force. In case of spring force, suppose this is this is the original length of the string, and when it is pulled by some force, the force acting on the spring is in the direction, in this direction. F force acting on the spring is in this direction, and when we pulls it and releases the string, after some time comes to an extension. Yes, here's the distance, which is x, and it is also the change in the extension of this spring. Some we have a equation that Fs is equal to minus k delta x, in which the minus k, which is also known as the constant, springs constant, and delta x is the change in delta x is change in extension, or we can also call it change in the compression. Here we this we also get that the change in extension can be mg by k, where mg is the force acting on the spring. There are the two types of the combinations in the spring. Combinations in the spring. First is parallel, in which the springs are attached in a way in parallel combination. The springs are attached in a way and in the second case is that they are arranged in the series. Series means yes, another. This is first string and this is second string. From these diagrams, we can get the uh, spring forces in the parallel and the series combination. As in parallel combination, the KF is equal to the combined force of the springs is K1 plus K2, where this is K1 and this is K2. In this case, this is K1 and this is K2. In the series combination, we get the spring force as 1 by common spring force is equal to 1 by K1 plus 1 by K2. Now we are going to study about inertial and non-inertial frame of reference. The difference between the inertial and non-inertial frame of reference is in the inertial frame of reference, those who is an observer is at a rest or at a constant velocity, but in the non-inertial frame, observer is accelerating with some accelerations. Frame of reference is just an perspective or the sight of seeing. In this also we had learned about a force called as pseudo force. Pseudo force is also known as a fictitious force. And we had a conclusion that what's the inertial frame? The inertial frame is equal to non-inertial frame plus pseudo force. So we will think that what is the pseudo force? Then pseudo force is mass of body into acceleration of frame. Acceleration of frame. Suppose here it is a trolley, and it is moving with something acceleration a. Here it is a block attached with a string, and here's another person. Suppose he is B and he is person A. Uh, the person A will see that the block is moving of mass m is moving with the acceleration a, but the person B will observe that the block is at a rest, and it has acceleration 0. And these are the frame of references. So to correct it, uh, Newton has stated as the pseudo force which acts. Suppose the acceleration or the force is acting on this block in this direction in F, then a pseudo force which is ma, then a pseudo force acts in its opposite direction of ma, in which the m is the mass of the body and a is the acceleration of frame. uh, and here we can also conclude that uh, the pseudo force always acts opposite direction to the acceleration of the reference. As we take this block as the reference is moving in this direction with acceleration a, the frame of reference is taken in its opposite direction. Now we will learn about constraint motion. Constraint motion part 2. We had learned about the constant motion part 1. Now we will learn about the constant motion part 2. In it we will take the some of the cases in which the suppose first case is uh, block is here, a block, suppose block B, and here pulley is attached, and here's an object attached with a string of and here the string is pulled with a velocity v. Then we can conclude that when the bigger block is at rest, this block also will move at a velocity v. Hence velocity of block is equal to v. And if we take the in the second case, when bigger block is moving with the velocity v, here the velocity v, and a pulley is attached here, uh, it is attached to the here, and a block is here. So in this, when the bigger block will move with the velocity v, the this block will also move here with v. uh, in this case the velocity of this block will equal to root 2 v, in which the tan theta tan theta's value is 1. We also had another case in which the both will move, the smaller block also and the bigger block also. In this case, when the bigger block moves with velocity v and the smaller block uh, moves with velocity. Here the string is pulled with the velocity v. Here's the object, and it is pulled with the v, and this block is also moving at the v. At this time, the velocity of this smaller block will be velocity of this smaller block will be root root pi v. In this tan theta's value will be 2v by 2, which is 2. In this case, when the bigger block moves with the velocity v, the smaller block is pulled with the velocity v. The velocity over this small block is the here v I cap plus vj cap, and here vi cap's value is 2, and sorry, yes, vi cap's value is 2, and vj cap's value here, I think vi cap, and here vj cap, the value of vi cap is 2, and vj cap is 1. Then by taking their root 2 square plus 1 square, we get here root 5 into v. Okay, sir. Sir.